Good morning. We were looking at how to make constant voltage sources. That is, in circuits for various places, we will need voltages that are constant. One example, of course, is the supply itself, which is expected to be constant, right? So we need first some source whose voltage remains constant. When I say constant, it should be across temperature, and if you also across process and supply voltage. Okay. So the first thought that came to us, because you're always asked to use, let's say, a constant VB of, let's say, 0.7 volts for operating point analysis in diodes and bipolar transistors, maybe you can use that 0.7 volts as a standard, right? Now, of course, this comes from the IV characteristics of a diode, which has the sharp exponential. By the way, in the reverse direction also, there is something called breakdown, which is also sharp. So even this could potentially be used as a constant voltage source, and it is used. It's called a Zener diode. Only thing is that voltage, first of all, is too large for most of our IC work. And on an IC, it may not be desirable to have junctions breaking down either. So it's not used very often. But the other one is, we looked at this. Now, the thing is, so if we do use something like this, the thing is, okay, it is roughly constant at 0.7 volts, but the temperature coefficient is minus 1.8 volt degree Celsius or so per degree Celsius. So we can consider 0 to 100 degrees as the normal operating range for most commercial purposes. So if you look at that, and if it is linear over that range, it's actually varying by 180 millivolts. The voltage itself is 700 millivolts. So it's a very large fraction of that. Okay. So it's actually not very useful because of its very high temperature sensitivity. Now, we can examine this VB a little further, and it turns out we can derive something that's actually constant or very close to being a constant. Okay. So this is basic device physics. You don't need to know the details. You can get this, but the final summary is what is most relevant. So we know that for a transistor biased at a current I naught, VB is VT log I naught by IS. Okay. Now, why does VB reduce with temperature? IS increases sharply with temperature. Okay. It increases substantially. That's why if you bias a transistor at a constant current, IS goes on increasing with temperature and VB goes on decreasing. Okay. Although, I mean, this factor here, VT, this is also proportional to temperature, but the increase in this is countered by the decrease in that substantially. Okay. So now let's look at some details of this IS. What does IS depend on? Do you know? Have you seen the expression for the saturation current of a diode or a bipolar transistor? Huh? So basically, it turns out that it is related to the mobility, and there is a factor KT, the standard Boltzmann constant and absolute temperature, and Ni square, which is the intrinsic carrier concentration. Now, we want to capture all of the temperature dependence to see what we can do with it. So what is the temperature dependence on a Ni square? Do you know that? It's not. So it turns out Ni square actually it is T cube and exponential Eg by kT. This is the band gap energy. Okay. I think, sorry, minus Eg by kT. By the way, this instead of writing it like this in terms of energy, we can also write it as a voltage, which I call the band gap voltage. It's the same energy gap divided by Q, the electron charge, divided by Vt, which is the thermal voltage we are familiar with, right? So now, this also depends on temperature. Okay. So it is basically, this goes as temperature to the some m, but m is approximately minus 3 by 2. Okay. So again, our goal is just to get a rough idea of the temperature dependence of these things, right? Not to study device physics here. So now, if you put everything together, this IS will be proportional to, first of all, you have T cube here, T there, and M there. M is negative, but whatever it is there. So it is, you have that, okay? And you have exponential minus VBG, which itself turns out to be dependent on temperature slightly, divided by Vt. Okay. And let me just club all the proportionality constants into some B or something like that, right? So now this VBE can be written as Vt log I naught by Is. So what do we get there? You get log I naught by B, that is one of the terms. T to the minus 4 plus m and exponential VBG by Vt. Okay. So now, if I expand this out, the first term I would just put it as VBG of T, and then you have this is some constant, right? And then I want to get this right. Four plus m log T. Okay. Is this correct? Sorry, there is a right. Now, this VBG itself has a nonlinear, it itself is a nonlinear function of temperature. You can get the equation from somewhere, but it can be roughly approximated to by a linear function. Okay. T, this is absolute zero, 0 Kelvin. This is VBG 0, and then after that it falls off. Okay. So again, the bottom line is, so because it is falling off linearly, it can be written as VBG0 minus C times the thermal voltage. I wish to keep voltage units there. VT is, I mean, I could have written C times T. Instead of that, I wrote C times VT, just absorbing the constants appropriately. Okay. So finally, we will have VBG0 plus VT times log I naught by B minus C minus 4 plus MVT log T. Okay. So you have a constant. Obviously, this is just the material property, right? It's basically the extrapolated band gap of silicon, or whichever material you choose to make the device in. For us, it is silicon at 0 Kelvin. Okay. Okay. And then this part is proportional to absolute temperature. It will eventually have a negative, I mean, it has a negative slope, but it's proportional to absolute temperature. And this is sum of the form T times log T. This is a non-linear term. Okay. So if you put all this together and plot VBE versus absolute temperature. Okay. So first of all, at T equal to 0, you will get basically the band gap itself. Okay, all the other terms go away, right? And then if you had only the linear dependence, it would have done something like that. Okay. And it turns out because of non-linearity, what happens is, the important thing also to remember is, this is 0 Kelvin. Of course, we are not going to operate anywhere near there, right? So let's just consider the regular commercial temperature range, which is, if I have to show the right scale, between 273 and 373. What is VBG0? What is the band gap of silicon? 1.1 electron volts or 1.1 volt at room temperature. The extrapolated value is closer to, at 0 Kelvin, is closer to 1.2 volts. Okay. So this is 1.2 volts. Now, if you also include this nonlinearity, what happens is that there is some curvature that you will see. Okay. Okay. So there is some nonlinearity. But now, what next? What is the constant that we try to extract? What did we want? What is the goal of this whole thing, discussion? To get a voltage reference. So now, where is the constant voltage reference in the equation? Is there something? VBG 0, right? That is a constant. Now, how do we extract that? The actual VB is VBG 0 plus a whole bunch of things. So what do we have to do to extract that one? We have to cancel out the other terms. Now, the predominant stuff is actually PTAT. Okay. And there is some nonlinearity. So if we cancel with the proportional to absolute temperature term, we are more or less done. This will cause some error. Okay. But still, this is the dominant deviation from VBG 0. So we try to cancel it. Okay. So it turns out that, and that anyway, I mean, I could have also explained it by simply saying that VB reduces with temperature, and I add something increasing with temperature and somehow make the slopes equal, and I will get more or less constant. But it's also good to know some more details. So now, basically, if you add a proportional to absolute temperature term, okay, only, what is the result? If the if this dependence was only linear, we would have got something like this. Okay, because I mean, two straight lines, they just sum to another straight line. But in reality, what you end up getting is, and again, we are interested in a limited temperature range, it will end up being something like this. It will have a small curvature. Okay, still the variation is quite small. It's in the order of millivolts, ideally. Okay, because there will be other errors also. Of course, you will have offset, you will have all kinds of other errors in the circuit itself. But this is just the inherent band gap. So this is what is called a first order band gap. That is, we only cancel the proportional to absolute temperature term. Now there are more sophisticated band gaps which try to cancel the curvature also, but we don't get into that. Those things need a lot of detail, and it's only rare that you even need that precision, and that needs actually very detailed knowledge of these temperature dependencies and so on. Okay, so this first order band gap is good enough. So there is a circuit which is called a first order band gap reference, or it's simply called a band gap voltage reference. Okay, so that is, you sum base emitter voltage with some constant times, let's say, the thermal. I mean, again, I could have written T. I just want to get voltage unit, so I'll write VT. Okay, so Cp times VT. So if I do this by adjusting Cp appropriately, you can imagine that you will cancel out the temperature dependence. I mean, that again, like I said, because VB is reducing, you can always think of adding something increasing. But what all this shows you is also that the actual correction needed is almost PTAT. So in fact, it makes it a very nice constant function. There is a small curvature, which basically, if you look at this value, the inherent variation would be a millivolt or less. Okay, whereas this reference voltage is 1.2 volts. That is 1 millivolt over the entire temperature range. So it's actually a very accurate reference. Okay, and very widely used. Right, every circuit will have it. Even digital ICs will have it because you will need references somewhere and so on. Okay, so now this is also easy for us to design because we already know how to make PTAT current, right? So let's go ahead. Any questions on this part? This device physics is not my forte. This is it's not my area, but basically this is just to give you some bare bones details of what's going on. Okay, so VBE reduces. There is a dominant proportional to absolute temperature component. There is also a nonlinear component that we ignore for now. Okay, so it's also easy to see that the resulting voltage will be basically the extrapolated band gap at 0 Kelvin. Okay. Now there are some details here which okay, one particular detail I will show. So one thing is here in this case, I have assumed I naught to be constant. Okay, but actually, if we make the PTAT cell, what is the nature of currents flowing through these bipolar transistors? Is it constant? It is obviously PTAT. Okay, so basically, let me show only that part. So here, so this is for constant I naught. Okay. What happens if I naught itself, if the current itself is PTAT? So then I will assume that the current in the bipolar transistor is of the form some I naught at a temperature T naught, but it is proportional to absolute temperature. Okay, right? So what will change? I will have to include this term here. Okay, so what changes here if I do that? So basically, this minus 4 plus m becomes minus 3 plus m, right? No, this T is here, T times. So basically, this will become 3 plus m, and then here with the same constants, I'll have T naught. Okay. So this is with P dat. But anyway, we will not use these equations directly for anything. Okay. So this is just to give you a flavor for the dependence. Okay. So anyway, this is what you would imagine, right? That is VBE versus temperature, let's say in the 0 to 100 C, 100 degrees Celsius, which is 273 to 373 Kelvin. VBE would do this with constant current. What would happen if the current is proportional to absolute temperature? It basically means that you have a higher current here than there. Okay. Let me assume that in the middle of the range, VBE is the same. I've adjusted the current to be like that. Okay. So then at as it comes close to 0, the current will reduce. So VBE will be smaller. And as it goes closer to 100, VBE will be larger. Okay. So so it also depends on how the current changes with temperature. Okay. So with PTAT, you will have a milder variation than with constant current. Okay. It's something to be known. But anyway, because we are using the PTAT cell, we can assume that the currents through our bipolar junctions, transistor junctions will be PTAT. Okay. This is something just to know. But still, everything else remains the same. We have a proportional to absolute temperature term which dominates, and we have a nonlinear term that we ignore. Okay. So finally, all we want to do is to realize something like VBE plus CP times the thermal voltage. Okay. Is this fine? Now CP is adjusted by simulation because many of these things depend on the process also. So what you do is, like I said, you will get a curve something like this. First you choose your temperature range, let's say 0 to 100 degrees Celsius. And then you adjust your CP so that, let's say in the middle of the range, 50 degrees Celsius, you get a flat portion. Okay. So that is the best case, right? So then the variation across the range will be smallest. Is that fine? So you basically adjust the temperature coefficient of this reference to be 0 in the middle of the range that you want. It's a pretty standard thing to do. I mean, you would like it to be 0 everywhere, but if you can't do that, you make it 0 in the middle so that across the range you have the smallest variation. This is okay? So now we can get on with designing the circuit that makes this. So our PTAT cell, the one we have so far, I will continue to show NPN transistors, but exactly the same thing will work with PNP, right? I will show this symbol to sort of indicate that it is a single stage op-amp. Okay. So now I think I called this VBE1. This is VBE2. And we know that the currents, both currents are the same. These are of course identical transistors. So I1, what is it? What was this is of course in the ratio 1:n. What was the value of the current? What is the value of the current? VT log n by R. Okay. Now what is it that we want? We want the reference voltage to be equal to some VBE plus some CP times VT. Okay. What would be the rough value of CP? That again you should be able to tell. What is the value of VREF that we get? What is it? this is 1.2 volts. What is the value of VBE at room temperature? 0.7. Okay. So what is it that you need from the other term? 0.5. So how much is VT? Roughly 25 millivolts. Okay. So what is the value of CP? 20. So CP should be roughly 20. Again, I emphasize that this is adjusted through simulations, because this is unlike, let's say, an inverting amplifier where we don't care too much about the exact characteristics of the device. The gain depends on the resistor ratio. This one depends on the device. Okay. But at least the rough order of magnitude you should have. Okay. So it can be quite a bit away from this, 18, 22, whatever. But let's say 20 is a reasonable number to take. So now how do we get this? We have to get VBE plus something that is proportional to absolute temperature. Now I have a circuit that gives me proportional to absolute temperature current. Okay. So how do I get that reference voltage? What should I do? Multiply what with the resistance? So what should I do in the circuit? So because PTAT currents are flowing here. Okay. So if I insert a resistor here, R2, so let me call this R1. What will be the voltage across this? So it will be VT log N R2 by R1. Okay, it is something proportional to VT. And now I can adjust R2 by R1 so that this whole thing log N times R2 by R1. So basically this is very log N times R2 by R1 is CP, whatever CP I require. Okay. So and what is this voltage? So let's say I call this V out equals VB1 plus VT log N R2 by R1. Okay. So all I need to do is adjust R2 by R1 such that this sensitivity with respect to temperature is 0 in the middle of the range. Let's say at 50 degrees Celsius for 0 to 100 degrees Celsius range. If the range is different, of course, you choose a different place to fix that. Okay. So if you do this, that's it. Like that's all our circuit, right? V out gives you this constant voltage if you adjust the value of R2 correctly or the ratio R2 by R1 correctly. Okay. What practical problem do you see with this circuit? Any source of error? What were the assumptions? I mean, we wanted the same current through the two branches, right? Is there some issue now? So M1 and M2 have very different VDSs now, right? Because how different are they? What is the difference in VDS? How much is that? Half a volt, right? This is that. Okay. So that's actually very different. So how do we fix this? What should I do to fix this? Cascode. Okay. What else? Is there some simple quick fix? Cascode will be fine. Only thing is cascode always takes more headroom, right? Because what is the minimum supply voltage you need to realize this? What is the minimum supply voltage with which this circuit can work? Let's assume that the op amp works with that, but just by looking at the PTAT cell, 1.2 plus VD sat, roughly 1.4, let's say, you need at least 0.2. So if you use cascode, that will go up. Okay. So what else can we do? So if we had equal VDS, source drain voltages, this problem won't be there. So how do we get equal source drain voltages for the two? Yeah, so very clear that I just put R2 there also. So if I do that, then I'm set, right? So then basically, this we can say is to, I'll modify this circuit. So you may still want to use a cascode for other reasons, but anyway, whatever it is, putting this resistor helps. Okay. Any questions about this? This is called this is the standard band gap voltage reference. And if you have played with circuits for whatever, any hobby related stuff, you may have seen band gap voltage references, or at least voltage references which have a value of 1.2 volts. The reason it's 1.2 is it is coming from the band gap voltage reference. Okay. And for any other voltage, you essentially make this and either attenuate it by some fixed ratio or amplify it by some known ratio. Okay. Now, the standard version is slightly different in that this also will work, of course. What is the voltage here at the drain of M2 in this circuit? What will be the voltage at the drain of M2? What is it? What's the voltage? I mean, why did we put R2 in the first place? It's the same. It's the same as the drain of M1, which is the reference voltage. Okay. So actually, in another variant, you can just connect these two together. Okay. So this is V out and this is also at V out, and you can just connect these two together. Now, why do this? What this does is basically here, of course, we made the VDSs of M1 and M2 equal, but still any mismatch between M1 and M2 will cause different currents to flow through this. That is a source of error. Okay. So that won't happen here if the op amp is ideal. Okay. Then the currents will be governed only by R2. Okay. If these two voltages are equal and these are tied together, that means that the current through this will be basically the same. Of course, the resistor mismatch will come into picture, but the resistor matching is better than transistor matching. So this one is better. Okay. So that is one thing. And by a similar token, you can show from analysis that the noise from these transistors don't come into picture. Okay. And actually, this circuit looks, the standard one may be written even somewhat differently, but now M1 and M2 basically they are a single transistor, right? They are just shown in parallel. What is this whole thing? This is a single stage op amp. What is that whole thing? I mean, have you seen that circuit before? It's basically if you have an NMOS differential pair followed by a PMOS transistor, that is a two-stage op amp. Of course, without the biasing, but now the thing is, this is not a general purpose op amp which has to like push current, pull current, and so on. The current is always only in one direction. Okay, so that's why there is no separate biasing source. But basically, this whole thing can be thought of as this is a two-stage op amp. And if you think of it as a two-stage op amp, its plus terminal is here at the bottom, and the minus terminal is there because this common source is inverting, right? So you can also write the same circuit. Okay, so you may see this also. Okay, this is exactly the same, right? So basically, this is you can use a two-stage op amp there, where the second stage is whatever transistor is providing this. Okay, but of course, it doesn't mean that you have to use only that op amp. You use any op amp here, it will work in the same way. Basically, it is going to force these two nodes to be the same. So this voltage will be whatever is required to force those two, right? That is the PTAT condition. And if you choose R2 correctly, that is the ratio R2 by R1 correctly, this voltage will be the reference voltage. Okay. I say two-stage op amp, but this doesn't mean you have to use only that kind of op amp. Whatever op amp works, you can use that. Is this okay? So the standard band gap reference may also be presented like this, okay, with an ideal op amp and this one. So then it works in exactly the same way. Hopefully, the way we went through all of these will make it very clear. Okay. Any questions about this? Now, of course, if the op amp has an output stage that can deliver a large current, so then you can connect your load directly here. That will be able to drive it. Okay, so that's also the reason to show this. Okay, because negative feedback will make sure that this is VREF. But then if you try to let's say draw a lot of current and the op amp cuts off or goes into some undesirable region of operation, you will have a problem. Okay, so that entirely depends on the output stage design. Okay, that is also the reason to tie these two together. Okay, let's say you are taking the output only from one side and you draw current. Okay, what happens is then M1 and M2 will be operating with different conditions. So that will also affect the matching. Okay, so this is okay for deriving the circuit, but invariably you use this. There are many other ways to get the same circuit also, but it's at least good to have some story. Whether it's the story that the inventors used to come up with the circuit or not, it doesn't matter. Any questions about this? So now we can get a constant voltage and we can scale this up to any value. Of course, it's not always that you need 1.2 volts. You may need something else, but we know how to make amplifiers, right? So if we want to make 5 volts, what do? We take this 1.2 volts, use let's say an inverting amplifier with a resistive ratio that gives you 5 by 1.2 as the gain, and then that's it, you're set. Any amplifier, inverting, non-inverting, whatever. Any questions about the voltage reference? What if I wanted a constant current? Everywhere, right? In every circuit, from analog circuits to this to RF, everywhere I'm sure you have seen current sources which are constant. But how do you get them? What do I need to get a constant current? Is it possible? Yeah, how? So one is, of course, one possibility is, now constant current is always more tricky. We'll see. One is you make a band gap reference. Okay, that is, this voltage is constant, right? And then you can use something like this. Let's say this is a source follower. This is a standard voltage to current converter, right? What will be this voltage? What will be that voltage? Vref. So what is the current? Vref by R. Okay. And this you can, so the current flowing through this is Vref by R. Now, you can't do anything about the temperature dependence of R. Assuming that R is independent of temperature, you will get a constant current. Okay. So this is the problem with all current references, right? There is no, unlike the bandgap voltage, so far as I know, there is no inherent current that is a constant that is available in the device. So you have to somehow relate it to the constant voltage, which is the bandgap voltage. So that means that it will be some voltage by a resistor. Whatever temperature dependence the resistor has, it will show up. Okay. So that there may be, I mean, you have to work around it. If you have, sometimes in a process, you have different resistors with positive and negative temperature coefficients. In fact, one of the assignment problems was for you to cancel the temperature coefficients. So by combining them, maybe different types of polysilicon resistors, you may be able to cancel. So there are a couple of variants of this. Another variant is so this you can do. That is, you convert, you make a voltage reference, and then so again here also you have Vref by R, and then you can directly mirror them by replicating the gate voltage onto other transistors. Okay. This of course can be done, right? Now the question is there any other way to do it also? Oh yeah, you have to use current mirrors also. Okay. By the way, I'm showing a version where the current is flowing this way. You can also have this can be turned into PMOS and that can be turned to NMOS and so on. So that is again possible. So, but basically this is what it is, right? Is it okay? Now, is there some other way also? How did we come up with the bandgap reference voltage? What was the idea? That is the circuit. What did we do? We had a VB that was falling with temperature, and to that we added this PTAT, which was increasing with temperature. Now, is there some other way of getting this current reference also? So let me again go back to the PTAT cell. Okay. So now, what are the currents flowing through M1 and M2? What are the currents flowing through M1 and M2? Vt log n by R1. So this is in the ratio 1:n. Okay. So now let us say that I have identical current sources Ix from both the nodes, from both sides. Okay. What happens to the currents flowing through the bipolar transistors? What happens to the currents flowing through the bipolar transistors? I mean, I added equal currents to the two sides, but I could add unequal currents also. What happens? What will be the current flowing through the bipolar transistors? Or okay, let me not complicate it by unequal current. Equal currents. What will be the current flowing through R1? I mean, regardless of whatever currents I draw from there, what is the current flowing through R1? So now the thing is, these MOS transistors are identical. Okay, so that means these currents are the same. Okay, and forget what I said about unequal currents. We draw equal currents. So that means the currents through the transistors will still be the same. So what is the difference in VBE? What is the difference? What's the voltage drop across R1? VT log N. Okay, if you have equal currents through the two transistors of size ratio 1:n, the VBE difference will be VT log N. Okay, it doesn't matter what the current is, right? So we still have, even in this case, the currents through the transistors will be in the with Ix. Okay. This part will still be the same. Okay. So now what will be the currents through the MOS transistors? What will be the currents through MOS transistors? It is VT log N by R1 plus Ix. Okay. Now earlier, the currents through the MOS transistors is proportional to absolute temperature. Now it is this proportional to absolute temperature plus something else. Okay. So is it possible to make this constant? What do we have to do? Ix is CTAT, complementary to absolute temperature. But what form should it be? What should be the value of Ix? Remember, we already know how to make a reference, right? So basically, Vref is VB1 plus Cp times Vt. Cp you can take to be a constant for your process, approximately 20, whatever it is. Okay. So now for this quantity to be constant with temperature, what should be Ix? Remember, basically this Cp is basically Vt log N R2 by R1, right? Let me write it here. So we already know how to design this. Okay. So this is constant with temperature over some range. Okay. So now we have Im1 equals Im2 equals Vt log by R1 plus Ix. How do I make this some constant with temperature? Just look at the expressions and tell me what Ix should be. Let's assume, of course, that the resistors are constant. Okay. What should be Ix? If you look at those two expressions, you should be able to tell, right? What is it? VB1 by R2. Basically, if I divide this by R2, what will I get? I get Vt log N by R1 plus VB1 by R2. Okay. Obviously, if this is constant with temperature and the resistors are independent of temperature, this also will be constant with temperature. Okay. So what should be Ix? Ix should be VB1 by R2. Okay. So how do I get that? How do I make Ix to be VB1 by R2? Is it possible? What is the what's the voltage across Ix here? VB1. So all I have to do is to replace Ix by R2. Okay. So right, this R2 is the same as whatever R2 you used in the earlier circuit to get a constant voltage reference. Okay. So this one now, IM1 and IM2 are VB1 by R2 plus VT log n by R1, which is basically 1 by R2 times VB1 plus VT log n R2 by R1, which is nothing but Vref, the band gap reference voltage. One thing I forgot to mention while initially deriving PTAT, it is PTAT only if the resistor does not have a temperature coefficient, right? That is, it is VT log n by R. VT log n is proportional to absolute temperature. If R varies with temperature, you will get some other temperature dependence. So the PTAT current is dependent on the resistors being temperature independent. And this current reference, this you can call this a current mode band gap. Here, this will work. You will get constant currents only if the resistors are independent of temperature. But the band gap voltage reference itself does not depend on that because it has VB1 plus this and a resistor ratio. Okay. So if both resistors have the same temperature coefficient, they will cancel out. The reference voltage, that's why it can also be meant more accurately. It doesn't depend on the temperature coefficient of the resistor. Okay. So they assume 0 TC for the resistors, whereas band gap voltage reference works with non-zero TC for the resistors because they just cancel out. You're only dependent on the resistor ratio. So we'll continue from there, but think about these things. And actually this current mode band gap reference was derived for a particular practical reason. Just think about it. That is, what is the minimum supply voltage required for this versus the band gap voltage? And is there a way to, earlier we said for the band gap voltage reference, you need 1.2 plus VD sat, about 1.4. Is there a way to get constant voltage with a lower supply? Because our supplies are actually already lower than 1.4. So we'll need that. Okay. Please think about these things. Any questions on voltage or current references?